Imagine standing in the middle of a vast ocean. Above you is the open sky. Below you is a deep, dark, cold world with almost no visible landmarks to guide the way. On the surface, people can rely on satellites. A ship can use GPS. An aircraft can use DPS. Even a small phone in your hand can know where it is on Earth. But when a submarine begins to dive beneath the surface, everything changes. The submarine leaves the familiar world of satellite signals. It leaves the sunlight. It leaves the waves above. It leaves the landmarks that humans normally use to understand direction. The deeper it goes, the weaker the light becomes. The surface turns into a faint glow far above. Around the submarine, there is only seawater, pressure, darkness, and silence. At that depth, GPS is almost useless. Not because the satellites stop working, not because the submarine has no receiver, but because seawater blocks the signal. GPS uses radio signals. These signals travel well through the air, but seawater absorbs them very quickly. After only a short distance below the surface, the signal becomes weak. As the submarine goes deeper, the signal fades, scatters, and disappears. Eventually, it is no longer strong enough to use. So when a submarine dives deep, it enters a world almost separated from GPS. Satellites are still orbiting Earth. The signals are still being transmitted. But between the satellites and the submarine, there is a massive wall of water. That water acts like an invisible barrier. So if there is no GPS, how does a submarine know where it is? How does it know which direction it is facing? How does it know how far it has traveled? And how can a massive machine move hundreds, or even thousands, of kilometers under the ocean without getting lost? The answer is not one single device. A submarine uses many systems at the same time. Each system measures a different part of the journey. One system tracks direction. One system measures motion. One system measures real speed using sound waves. One system listens to the ocean. One system compares the shape of the seafloor. And when truly necessary, the submarine can rise close to the surface for a short time to update its position with GPS. The heart of underwater navigation is the inertial navigation system. In simple terms, this is the main brain that helps the submarine calculate its own position without asking satellites. Before diving, the submarine already knows its starting position. From that starting point, the computer inside the vessel begins recording every movement. How long the submarine travels forward, how much it turns left, how much it turns right, whether it pitches down or rises upward, whether it speeds up or slows down. All of these changes are measured continuously and sent into the navigation computer. Imagine walking inside a large room with your eyes closed. You know that you started at the door. Then you walk 10 steps forward. You turn left. You walk 20 more steps. Then you turn right. If you remember every step and every turn, you can still estimate where you are, even without seeing anything. A submarine works in a similar way, but instead of counting footsteps, it measures movement with extremely sensitive sensors. And instead of moving inside a room, it moves through the three-dimensional space of the ocean. To know how it is turning, the submarine uses gyroscopes. A gyroscope helps the vessel understand how its body is rotating. Is the bow turning left or right? Is the submarine pointing downward or upward? Is the hull rolling slightly to one side? These changes can be very small, but during a long underwater journey, even a tiny error can grow into a large distance. If the bow is off by only a small angle, and the submarine continues traveling for hours, the final position can be far away from where it should be. That is why gyroscopes constantly measure the submarine's orientation. They do not only measure direction, they measure turning, tilting, pitching, and rolling in three-dimensional space. When the submarine turns left, orientation data is sent to the central computer. When it turns right, the data is updated again. When the submarine dives deeper or raises its bow toward shallower water, the system keeps tracking every change. Because of this, the submarine always knows the attitude of its own body. It does not need to see the sun. It does not need to see the stars. It does not need to see the horizon. Outside, there may be nothing but endless dark blue water. But inside, the system still knows where the submarine is pointing. However, knowing direction is not enough. A submarine also needs to know how it is moving. Is it accelerating? Is it slowing down? How far has it traveled? Is it moving steadily or changing speed? That is the job of accelerometers. An accelerometer measures changes in motion. When the submarine starts to speed up, the sensor detects it. When the submarine slows down, the sensor detects that too. When the submarine moves steadily for a period of time, the data can be used to calculate speed and distance. The navigation system combines data from gyroscopes and accelerometers. Direction tells the system where the submarine is facing. Acceleration tells the system how the motion is changing. Time tells the system how long that motion has continued. From these three things, the computer can calculate a new estimated position. Second by second, the system updates itself. Every small movement of the submarine is recorded. The vessel does not need to look outside to know that it is moving. It estimates its position from everything that has happened since the starting point. But this is where the problem begins. No sensor is absolutely perfect. A measurement can be slightly off. A rotation angle can contain a tiny error. An acceleration reading can be just a little inaccurate. At first, these errors are almost invisible, but underwater journeys can last a long time. Hours, days, sometimes even longer. And as time passes, small errors begin to build up. A tiny error in direction can make the route drift. A tiny error in speed can make the calculated distance different from the real distance. Each small error is like a tiny grain of dust. One grain does not matter much, but after enough time, the dust can become a thick layer. The same thing happens with inertial navigation. The longer the submarine travels without checking against outside data, the more the estimated position can drift away from the real position. That is why a submarine cannot rely only on its internal navigation brain. It needs other systems to check and correct the estimate. One of the most important systems is the Doppler Velocity Log, often called DVL. DVL measures speed using the Doppler effect. The basic idea is simple. The submarine sends sound beams from the underside of its hull down toward the seafloor. The sound travels through the water, hits the seafloor, and reflects back. When the signal returns, the system measures how it has changed. From that change, the computer can understand how fast the submarine is moving relative to the seafloor. The important point is this: DVL does not only depend on sensors inside the submarine. It measures the submarine's motion relative to the outside environment. If the internal system thinks the submarine is moving at one speed, but DVL measures a slightly different speed, the navigation computer knows that a correction may be needed. DVL data is like a message from the outside world. It tells the navigation system how the submarine is actually moving. Because of that, errors from inertial navigation can be reduced. When the seafloor is close enough, DVL can use it as a very good reference point. At that moment, the seafloor is like the ground beneath your feet. The submarine cannot see it with human eyes, but it can sense it with sound. Sound beams travel downward. Echoes return upward. The measurement cycle repeats again and again. From this, the submarine can better understand its real speed, direction of drift, and travel distance. But the seafloor is not always close. Some parts of the ocean are extremely deep. The seafloor may be far below the submarine. In those areas, the sound signal may become weaker before a clear return is received. In that case, DVL can also measure relative to the surrounding water mass. This is not as stable as measuring against the seafloor, because the water itself may move with ocean currents, but it still gives the navigation system more information. In other words, DVL is a reality check. It helps the submarine compare its internal estimate with the outside world. But under the ocean, speed and position are not everything. The submarine also needs to know what is around it. Is there dangerous terrain nearby? Is there an obstacle ahead? Is there another vessel in the area? In the darkness of the deep ocean, light does not help very much. Cameras are limited, so the submarine uses sound. This is sonar. Sonar can be understood as the use of a submarine. It helps the vessel listen to the world around it. Sound can travel through water much better than light in many situations. A sound wave can travel through the ocean, reflect from objects, and carry information back. There are two main ways to use sonar: passive sonar and active sonar. Passive sonar is the quieter method. The submarine does not send out a signal. It only listens. It listens for distant engines. It listens for propellers. It listens for water moving around another hull. It listens to the natural sounds of the ocean. From these sounds, the system can detect whether something is moving, where the sound is coming from, and sometimes even what kind of source is making it. Passive sonar is extremely important because it helps the submarine remain silent. For a submarine, silence is a major advantage. If the vessel makes too much noise, it may be detected. That is why, in many situations, a submarine prefers to listen rather than transmit. It is like a person standing in the dark without turning on a flashlight, listening carefully to every sound nearby. The quieter it remains, the harder it is to find. Active sonar is different. When using active sonar, the submarine sends a sound pulse into the water. The pulse travels outward. When it meets terrain, an object, or another vessel, it reflects back. From the returning echo, the system can estimate distance, direction, and shape. This allows the submarine to see with sound. It can detect underwater rocks. It can scan terrain ahead. It can build a three-dimensional picture of objects around it. But active sonar has a major weakness. When the submarine sends sound into the water, other vessels may hear it too. It is like turning on a flashlight in the dark. You can see more clearly in front of you, but others may also see you. So a submarine cannot always use active sonar freely. It must choose carefully. If safety is the priority at a complex area, active sonar can be very useful. If stealth is the priority, the submarine may rely more on passive sonar and quieter systems. But no matter how it's used, sonar plays an important role. It helps the submarine understand its surroundings. It helps detect terrain and obstacles. It can also support navigation when combined with other systems. Under the ocean, where light fades meter by meter, sound becomes an extremely valuable tool. A submarine does not see the world the way humans see with eyes. It senses the world through sound waves, reflections, data, and calculation. Another important tool is the seafloor map. The bottom of the ocean is not a flat empty surface. It has underwater mountains. It has deep trenches. It has valleys. It has long ridges. It has slopes. It has complex high and low areas that can stretch for hundreds of kilometers. In a three-dimensional model, the seafloor looks like a massive hidden landscape in the dark. These terrain features can become landmarks. Not visual landmarks, but shape landmarks. An area with a deep trench is different from an area with underwater mountains. A long slope is different from a flat plain. These features can be stored in a map. When the submarine passes over an area, it can scan the terrain below. Then the system compares the newly measured terrain with the stored map. If the shapes match, the submarine can confirm where it is. This is called seafloor map matching. It is similar to recognizing a familiar road by its shape. You do not need a road sign. You do not need GPS. If you see the curve, the hill, or the line of trees that you know, you can guess where you are. Underwater, the idea is similar. The submarine cannot see the road with human eyes, but it can compare the shape of the seafloor using data. If the map is accurate and the terrain is distinctive, this can be a powerful way to correct position. When the measured terrain matches the stored map, the system can pull the estimated position closer to the real position. A slightly drifting route can be corrected. Accumulated error can be reduced. The navigation path becomes more stable. But this method also has limits. If the seafloor is too flat and has few features, matching becomes harder. If the stored map is old or lacks detail, the results may be less accurate. That is why seafloor mapping does not work alone. It is one part of a larger navigation network. Now look at the whole system. The inertial navigation system calculates position from inside the submarine. Gyroscopes help keep direction. Accelerometers measure changes in motion. DVL measures real speed using sound waves. Sonar helps sense the environment. Seafloor maps help match position with terrain. All of this data is sent to the central computer. The computer does not receive only one answer. It receives many sources of information. Then the system compares, combines, and adjusts them. If inertial navigation begins to drift, DVL can help pull it back. If speed is uncertain, acoustic data can add more information. If the terrain below is clear, the seafloor map can confirm the position. If the area ahead is complex, sonar helps the submarine understand what it is entering. No single system is perfect, but when many systems work together, they cover each other's weaknesses. That is why a submarine can travel in an environment where GPS cannot work continuously. However, even with advanced internal systems, there are times when the submarine needs a very accurate outside reference. That is when GPS returns. But not in the same way we use GPS on land. A submarine does not keep GPS running continuously while it is deep underwater. Instead, it only updates for a short time. When needed, the submarine can rise close to the surface. It does not have to fully surface. It only needs to reach the right depth and raise a small antenna or periscope above the water. In that brief moment, the antenna can receive GPS signals from satellites. The signal is sent into the submarine. The navigation system receives a more accurate position. The accumulated error from the underwater journey can be reduced or reset. After the update is complete, the antenna retracts. The submarine dives again, and it continues its mission in silence. The whole process can be very short, but it is extremely valuable because it gives the navigation system a fresh reference from the outside world. The important point is that GPS is not the main guide when the submarine is deep underwater. GPS is more like a quick check, a position confirmation, a way to refresh accuracy after a long period of self-navigation. For most of the journey, the submarine depends on itself. It depends on sensors. It depends on sound. It depends on the seafloor. It depends on calculations repeated again and again. If we look at the entire journey from beginning to end, everything works as a tight sequence. First, the submarine starts from a known position. Then it dives. GPS disappears. The inertial navigation system begins calculating position. Gyroscopes tell the system where the submarine is facing. Accelerometers help calculate motion and distance. DVL checks real speed against the seafloor or the water mass.